Hi, my name is Sachin Takmare, and you are welcome to the 16th video of this series. In the previous video, we learned GRU, Gated Recurrent Unit. Along with that, we have seen what sequence-to-sequence data is. In simple terms, sequence-to-sequence data refers to a type of problem where the input given to the model is sequential data and the output generated by the model is also a sequential data. We discussed machine translation as an example. However, handling sequence-to-sequence data effectively using RNN, LSTM, and GRU architectures was quite difficult. Researchers continued their work, and in 2014, three researchers from Google published a research paper titled Sequence-to-Sequence Learning with Neural Network. In this paper, the author introduced an architecture called the Encoder-Decoder architecture. The journey that started from this single paper eventually led to modern AI systems such as ChatGPT. In this video, we will discuss this research paper and the encoder-decoder architecture in detail. The authors pointed out the important limitation of traditional neural networks. Traditional neural networks usually accept fixed size input and generate fixed size output. But in real world applications, the input and output are often different. For example, suppose we want to translate the English sentence, I love India. The input contains 3 tokens. Its Hindi translation could be, मैं भारत से प्यार करता हूँ, which contains 6 tokens. Therefore, the authors argue we need a model that can handle variable length inputs and variable length outputs. To solve this problem, they proposed a model called encoder-decoder architecture. Using LSTM, this architecture contains 3 important components. First is encoder, second is decoder, and third is context vector. The encoder receives the input sequence and converts it into fixed length vector. In simple words, it creates a summary of the entire input sequence. This summary is called the context vector. The decoder then uses this context vector to generate the output sequence. This was the architecture proposed in this paper. The authors used this model for machine translation, especially English to French translation. They trained the model using a large dataset contains English sentences and their corresponding French translation. The training was performed using a supervised learning approach. They also made an interesting observation. They found that reversing the input sentence improved the performance. This happened because the model was able to learn dependencies more efficiently. In simple words, after this research paper, machines become capable of understanding one sequence and generating another sequence. Now, let us understand what exactly the encoder and decoder do. Imagine that you want to translate a Marathi sentence into French, but you do not know French and your friend does not know Marathi. However, both of you know English very well. What will you do? First, you translate the Marathi sentence into English and write it on a paper, the piece of paper. Then you give that paper to your friend. Your friend reads the English sentence, understand its meaning, and then explain the same meaning in French. In this example, you are the encoder, your friend is the decoder, and the piece of a paper is the context vector. The encoder's job is to read the entire input sequence and store its complete meaning inside a fixed sized vector. This vector is called the thought vector or the context vector. The encoder reads the complete sentence before passing information to the decoder. The context vector is the heart of this architecture. All the information extracted by the encoder is stored inside this small vector. in summarized form. After that, the decoder starts its work. It takes the context vector and generates the output sequence one token at a time. This process continues until the complete output sentence is generated. Friends, before the encoder-decoder architecture, the most models requires the input and output lengths to be similar. But this architecture allows us to handle sequences of different lengths. For example, a Marathi sentence containing 5 words may become an English sentence containing 8 words. This flexibility become possible because of the encoder-decoder architecture. However, this architecture also had some limitations. One of the biggest limitation was context vector itself. The entire responsibility of generating the output was placed on this single context vector. If the input sequence become longer than about 30 tokens, the context vector started failing. This problem is known as the bottleneck problem. Let us understand this bottleneck problem with simple example. Imagine that you are going to attend a wedding. You have 10 pairs of clothes, 3 pairs of shoes and many other important items. But there is one condition. You must fit everything into a small handbag. What will happen? If you have only a small amount of luggage, you can manage to fit everything inside the bag. But if you have too many items, you will force to leave something behind. Later, when you need one of those missing items, you will realize that it was never packed in the bag. Exactly the same thing happens with the context vector. The decoder can only use the information stored inside the context vector. For very long sequences or sentences, the encoder cannot compress every important detail into a single fixed length vector. As a result, some information is lost. And because of the decoder depends entirely on the limited context vector, it cannot generate highly accurate output. Now think about it. If the input sentence contains 50 words or even 100 words, how much information can a single context vector really store? Naturally, it starts forgetting important details. This leads to translation errors and poor output quality. Researchers realized that this was a major challenge. They continued their research and proposed a new idea. They asked an important question. Instead of forcing the decoder to depend only on the context vector, what if we allowed it to pay attention to entire input sequence whenever needed? Around 2014 and 15, the answer to this question emerged, and that answer was called attention mechanism. This mechanism completely changed the game. The decoder was no longer trapped inside a bottleneck problem. While generating the output, it could directly look at different parts of input sequence whenever required. It could give more attention to important words and less attention to less relevant words. But how exactly does this happen? How does the decoder knows which words deserve more attention? And how did this single idea create a revolutionary transformation in the field of AI? We will explore all these questions in the next video of this series. Friends, we have now reached the final stage of our storytelling journey, Neurons to ChatGPT, the complete journey from Neurons to ChatGPT. If you would like to continue this journey with me, follow and subscribe the channel and share this with your friends who are really interested in learning AI. I will see you again in the next video of this series. Thank you for watching this video. Bye.